Hello, geometry students. Today's lesson is about finding the areas of regular polygons and composite figures. Now, regular polygons are something we've talked about earlier this year. If you will recall, a regular polygon is a polygon who has all congruent side lengths and all congruent angles. So over here to the right of the box, you can see a picture of a regular pentagon. It has 5 sides, and all 5 sides are congruent to each other, and all 5 angles are congruent to each other. So this is a figure that we could find the area of now using our new formula we're going to learn today. So composite figures we'll talk about in just a moment, but basically a composite figure is a combination of 2 or more other figures that we have found areas of before. So we're adding them up or sometimes even subtracting one from another. So in the box is our important information. First, the area of a regular polygon. If a regular polygon has an area A of A square units, a perimeter of P units, and this is a new word, apothem, or some people say apothem, I like to say apothem, of A units, then we use this area formula. The area is equal to 1/2 little a, which is what the apothem is, times capital P, which is your perimeter. So this formula is on the geometry formula chart. It's not one that needs to be memorized. And we probably ought to figure out what this new word apothem means in order to use the formula, because we know what area means and we know what perimeter means. The little a for the apothem is going to be, well, we've got it up here in bold. In a regular polygon, the segment drawn from the center of the polygon, so this dot point A is our center, perpendicular to the opposite side, so you're going to see a right angle indicating that it's perpendicular, is called the apothem. So this segment from A to P is the apothem of this pentagon. So now we're going to go down here and do some practice problems involving this formula. We're going to find the area of each regular polygon and round to the nearest tenth if needed. So our first problem here is a triangle, a regular triangle, so that would be an equilateral and equiangular triangle. The problem with this this exercise is that they don't give us all the information that we need in order to solve the problem. All we know is the side length. So the side length will help us to find the perimeter. The perimeter is going to be this side 14 multiplied times 3. Since they are regular polygons, all the sides are the same. So if there's 3 sides that are each 14 units long, then our perimeter is 42. Now, we need to find the apothem, which is this little side A, from the center perpendicular to the side here. So the entire length of the side is 14. And this apothem meets the side at its midpoint. So this side of the triangle on the bottom here is 7. Okay, this is 7, and this would have to be 7 over here. Now, this is a special triangle because, if you'll remember, there's 180 degrees in a triangle. So if all 3 of these angles are the same, 180 divided by 3 is 60. So this is 60, and this is 60. And this segment from the center to the vertex of the triangle divides this angle into 2 congruent angles. It bisects it. So this angle is 30. And if this angle is 30 and this one is 90, then this remaining angle, in order to create 180 degrees, would have to be 60. So this is our special 30, 60, 90 special right triangle. We have information about that on our formula chart. We learned about that earlier this year. So if we know that this long leg is 7, we're going to need the short leg. If you're going from a long side to a short side, you divide, and the number that you divide by, which is on your formula chart, is the square root of 3. 7 divided by the square root of 3 will give you the length of that apothem side, which comes out approximately to 4.0. Use a calculator. Any calculator will do. So now the area is equal to our new formula, 1/2 little a times capital P. Important to use a little a for the apothem and a capital A for the area so we don't mix those two quantities up. So we're trying to find the area. We're going to fill in 4 for the apothem that we just calculated and 42 for the perimeter that we also calculated. And if we multiply 1/2 or 0.5 times 4 times 42, this equals 84. And since the side length was in meters, the area will be meters squared. That's the answer to number 1. All right, that was a particularly challenging problem because neither the apothem nor the perimeter was given, and we had to recall some information we learned earlier this school year about special 30, 60, 90 right triangles to solve the problem. Number 2 is going to be quite a bit easier than number 1. So they have the apothem given up here at the top. That's what this little a is for. That's the length of our apothem right here from the center perpendicular to the side. And it doesn't have to go down. The apothem could actually go to any side. It would be exactly the same for each. But they did not give us the perimeter. The side length is 10, and all the sides are the same, and there are 5 of them. This is a pentagon, so 10 times 5 is a perimeter of 50. Now, the area is 1/2 little a times P, so 1/2 times the given apothem, 6.9, times the perimeter, 50. And when you multiply that, you get 172.5. And the units, since they were in inches for the side length and the apothem, the area is measured in inches squared. Okay, number 3. We have a square. And you might say, wait a minute, Mrs. Heiss, we've already found the area of a square. Isn't it just base times height, or take any side and square it? Well, yes, that does work. But I'm going to show you that you can also use this formula, the area equals 1/2 the apothem times the perimeter, to find this value, just so that you can see there is more than one way to solve this problem. So, to start, we're going to find that perimeter. The perimeter is going to be 15 times 4, since the sides are 15 units long and there are 4 of them. So that's going to equal 60. The little apothem on the square, since this is at the center, is exactly half the length of the side, because from here to here is the same as the length of the left side or the right side, because the sides are perpendicular on a square. So to get the apothem, we're going to take 15 and divide it by 2, which gives us 7.5. And now we'll substitute those values into the formula, 1/2 little a times P. So 1/2 times 7.5 times the perimeter of 60 gives us 225, and the units would be inches squared. Now, what would we have gotten if we'd done base times height? The base is 15. The height is also 15 because all the sides on a square are the same. 15 times 15 does equal 225. And yes, I agree, that would have been an easier way to solve the problem. But it's just interesting to see that the math that we're learning new coincides with some things that we've learned previously. And there's more than one way to approach a problem. So, number 4. This shape is a hexagon, 6 congruent sides. They gave us the apothem, which is wonderful, but they did not give us the length of the sides. So this one is going to be like number 4, a little bit of a challenging problem. Now, this triangle that they made here, this right triangle, is a special right triangle. Some of you may remember from our unit on polygons that each angle of a regular polygon is 120 degrees. We use that fact quite a bit this year. If you don't remember, you couldn't always use the formula for the angle, the degree measure of a regular polygon, which we learned was n minus 2 times 180 divided by n. So we have n for the number of sides, 6 sides minus 2 times 180 divided by the same 6 sides. So if you take 4 times 180 and then divide by 6, that will equal 120 degrees. So you can calculate that value using the formula that we learned when we studied polygons. So that tells us that this is a 120 degree angle. Each one of these is 120 degree angles. And this segment from the vertex to the center of the circle bisects the angle. So it splits it in half. So this is 60 and this is 60. So this is 60, this is 90, this is 30. Here come the 30, 60, 90 special right triangles again. So we know the length of the long leg is 5 square root of 3. And we want to know the length of the short leg. So we divide to get the smaller number, and the number we divide by is the square root of 3. Well, if I take 5 square root of 3 and divide it by the square root of 3, the square root of 3 just cancels out. It divides out, it equals 1. So this side is 5. Now, that is not how long the whole length of the side of the hexagon is, because this is just this short leg of this triangle. But since the apothem meets the side at the midpoint, that means the other half of the side is also 5, and so this entire side length is 5 plus 5, which would give us 10. So to find our perimeter, we're going to say, okay, each side is 10, and there's 6 sides on this hexagon. So 6 times 10 equals 60. And the area is going to equal 1/2 times the apothem, which they gave us, 5 square root of 3, times the perimeter, which is 60. And if you multiply those together, you are going to get a decimal, obviously with this square root of 3. So we will round to the nearest tenth according to the directions, one number after our decimal. That's going to be 259.8, and then centimeters squared for our units. All right, number 5. This is an octagon. There are 8 sides here. They gave us the apothem, which is wonderful. They also gave us the side length, but we need to find the perimeter. So if there are 8 sides and each one is 10 units long, we do 10 times 8, which gives us 80 for our perimeter. And now area equals 1/2 little a times p is our formula. So area equals 1/2 the apothem, which is 12.1 given in the problem, times the perimeter that we just found, 80. And multiplying this gives us 484. And the units would be inches squared. Okay, next, number 6. This problem is another hexagon, sort of like number 4. So, the same fact that we just talked about, that each angle of a hexagon is 120 degrees, still stands. We do not, this is a particularly challenging problem because we do not have the length of the side and we do not have the length of the apothem. This 4 is not the apothem. The apothem goes from your center to the midpoint of the side at a 90-degree angle. So this is the apothem here. This is the radius of the circle that goes all the way around the hexagon. So we know that radius is 4. That radius is also the hypotenuse of this special right triangle. Since this big angle of the regular hexagon is 120 degrees, the radius splits this angle into 2 congruent parts. It bisects it. So this side is 60 and this side is 60. And this last angle in this special right triangle has to be 30, so that if you add 30 plus 60 plus 90, you get 180. So from our 30, 60, 90 special right triangles, if we know the length of the hypotenuse, we divide it by 2 to find the length of the short leg. So this short leg right here is going to be half of 4, which is 2. That's still not the side length, but that means this other side would have to be congruent. It'd also be 2, and we add those two numbers together to get 4 for the side length. Now, we can find the perimeter. So the perimeter is going to be 4 times 6, since each side is 4 units long, and there are 6 of them. So 4 times 6 equals 24. So 24 is the perimeter. And now to find the length of the apothem, we're going to take our short leg, which was 2, and since we're going to the long leg now, we're going to the bigger side, we're going to multiply it by that special number, square root of 3. So the apothem equals 2 times the square root of 3. And you can multiply that and get a decimal, or you can just leave it 2 times the square root of 3, kind of like we had 5 times the square root of 3 for our apothem on number 4 over here. So our area is 1/2 little a times capital P. So area is 1/2 times 2 square roots of 3 times 24. And if you multiply all that together, that should equal, rounded to the 10th place, 41.6. And since these units were meters in the problem, it would be meters squared for the area. And there we go. Now let's go on to the areas of composite figures. So, when we're finding areas of composite figures, it's often a sum or a difference of known areas. So for example, this little A here was a rectangle where we cut out half of a circle. So we'd find the area of the rectangle, find the area of the half circle, and subtract to find that shaded area. On B over here, you'd find the area of the big rectangle, and then find the areas of these 3 circles and subtract the total rectangle minus the 3 circle areas. So each problem can be a little bit different. Sometimes they require a little bit of thinking to figure out what shapes we need to add or subtract in order to do the problems. Number 1. Here we have a rectangle and a half circle added on. So the first thing you want to do when we're finding the area of these composite figures is identify the shapes that you're working with here. So we're going to find an area of a rectangle, and we're going to add it to the area of a half circle, which is also called a semicircle. So now we need to figure out what formulas we use for these shapes. These are all going to be formulas that we've used earlier this year. So the area of a rectangle formula is base times height. Feel free to look at your geometry formula chart also to help you. Plus, the area of a half circle is going to be the area of a regular circle, which is pi r squared, times 1/2, or you can do divided by 2, or times 0.5. So, how long is the base of our rectangle? Well, that's going to be 34. And the height of our rectangle right here is 15, plus 1/2 times pi times the radius. Well, the radius of the circle is halfway across the circle. We know all the way across the circle is 15. So if you do 15 divided by 2, that's 7.5 for the radius, and that gets squared. So we type that into the calculator and round to the nearest tenth. So that answer comes out to 598.4, and the units are feet squared. Okay, number 2. We have a couple of ways to look at this problem. If you notice that if you were to connect along the top and connect along these vertices down here, these are congruent triangles. So it's like you took the one on top and slid it down and stuck it on the bottom. So you technically could find this just by finding the area of this rectangle, base times height, 40 times 24. That's one way to do it. Base times height, 40 times 24, and that would give you 960 inches squared. Another way to do this problem is to say, no, I think I need to find the areas of these two shaded quadrilaterals and add them together. Now we know they're congruent also, so we could double it, but you could do like the base times height of one plus the base times height of the other, or 2 times the base times the height. Now, remember the height has to be perpendicular to the base for a parallelogram. So let's say that if I turn my paper sideways, the base is 24. The height would have to be the distance from the vertex to the top at a 90-degree angle, which would be half of 40, which would be 20. So the height would be 20. This would be a base of 24 times a height of 20, plus the other one is congruent, so another base of 24 times a height of 20. And if you do that, you get 960 inches squared also. So I point out that there's 2 ways to work this problem. Could be even more than that, really. Some of these can be done in multiple ways, and it's fine if you do it a different way, as long as you end up with the same result. You're using your math correctly. All right, number 3. On this one, I am going to break this complicated shape into 2 triangles. There's this one on the right, and then there's the one that I did not highlight on the left. So I'm going to add 1/2 base times height plus 1/2 base times height. That's your area of a triangle formula. So the base of the one on the left is 38. And the height, remember, is perpendicular to it. You'll always see your right angle. That's 14. Plus 1/2 times the base of the highlighted one that I just highlighted is 40. And the height, perpendicular to it with the 90-degree angle, is 10. So then we can just type that in our calculator, and we get 466 centimeters squared for our area. All right, let's take a look at number 4. On number 4, this actually might be a good place for you to pause your video and try to do this one on your own, and then push play again to see if you got it right. First, identify the shapes. We have a square and we have a triangle. So we're going to do our area of the square plus the area of the triangle. Oops. Now, the area of a square, that's base times height. The area of the triangle is 1/2 base times height. So the base and the height of the square are 22 and 22. All these sides are the same. So it's 22 times 22. Now, the area of the triangle is 1/2 times the base. Oh, base of the triangle. Okay, that's going to be right here, which would be the same as the sides of the square, 22. And the height of the triangle is going to be this perpendicular distance from the base to the height. Since I know this much is 22, I'm going to take 42 minus 22 to give me the height of my triangle, which will equal 20. And now if we put all that together in our calculator, we will get 704 centimeters squared. All right. Number 5. On number 5, we have 2 quadrilaterals. Do you remember what the names of these quadrilaterals are? These are trapezoids. So we're going to do 2 times the area of the trapezoid. And the area of a trapezoid formula is on your geometry formula chart. We've learned it recently. 1/2 times base 1 plus base 2 times the height. So now we just need to fill in what we know. 2 times 1/2 times the bases are the perpendicular sides. So 20 and 40. And it doesn't matter whether I put the 21st or the 41st. You can do it either way. They're just being added, so they'll add up to the same either way. And then the height is the perpendicular distance between the parallel sides. We do not have that given, but we do know that the height from this parallel side to the opposite one is 64. And since these are congruent trapezoids, we can divide that by 2. Half of 64 is 32. And now if you type that in your calculator, the result will be 1,920 meters squared. All right, last one. This is another one that can be done a couple of different ways. I'm going to do it as 2 congruent triangles added together. So 2 times the formula for the area of a triangle, 1/2 base times height. How do I know these triangles are congruent? Well, you see these parallel lines? That means your alternate interior angles are congruent. And these are vertical angles, so these are congruent. And we have congruent sides here. And this angle has to be congruent because the third angle theorem says if 2 angles of a triangle are congruent, the third angles must be congruent also. So I could say by angle, side, angle, these triangles are congruent. So now we need to figure out what the base and the height would be. Well, the base is going to be 35. 1/2 times 35. And the height is going to be, just for one triangle, because I'm doubling it, half of 15, because 15 goes all the way from this base to this base. So I'm just going to the middle to get my height. Half of 15 is 7.5. So 2 times 1/2 times 35 times 7.5 equals 262.5. And the units would be square yards. Okay, that's our lesson on finding areas of regular polygons and composite figures. So good luck with your assignment, and let me know if you have any questions. I would be happy to help. Have a great day. Bye.